Focus on some research I've been doing with Bill Gropp. The basic goal of this research is to develop conjugate gradient methods that perform well at extreme scales. So basically the motivation behind this is that ideally it'd be nice if the methods we use on our desktops and so on performed great on extreme scales. In practice, we're probably not going to be that fortunate. We're probably going to need to develop methods that perform better, or that better deal with the issues that we run into at scale. So in particular for preconditioned conjugate gradient method, the dot products limit scalability because they're a synchronization point. In particular, if we use non-blocking methods that replace the blocking Allreduce with a non-blocking Allreduce, we have the potential to avoid the synchronization cost due to performance variations across cores. Basically, it allows us to deal with noise in the systems. There's also some possibility to hide most of the cost of the Allreduce. The Allreduces are pretty efficient, but it's still a way we can improve performance a bit. So basically, the main goal, can we develop non-blocking PCG methods capable of performing more efficiently than standard methods at scale? So to give you a quick overview of this, I'm first going to go over some conjugate gradient methods that we looked at. In particular, I'm going to go into a bit more detail on PCG and NBPCG, which is a non-blocking method we've been working with a lot. I'm going to go over some performance modeling for these methods so that we can better understand how they should ideally perform. And then go over some results on blue waters. And finally, go over an initial approach we have to modeling noise with our model. So basically, this is the general idea behind PCG. Most of you are probably pretty familiar with it. In general, it's basically an efficient algorithm for solving large sparse systems of linear equations where A is symmetric, positive, definite. It's probably a bit better to look at the algorithm itself and basically note the key places where we're spending time. So generally, the two most time-consuming parts are the matrix vector multiply and the preconditioner. Additionally, there are two Allreduces in here, which it's important to note they're blocking. So if the processors end up taking different amounts of time to do the previous operations, they will get to the Allreduce and they will wait. But one of the nice things about PCG is that it's fairly easy to rearrange the method so that we can change the ordering of these operations. So there are three different variations of it that I've been looking at. The first is L56 PCG. This is based on LePac working note 56. Basically, this performs both dot products at the same time. There's also two non-blocking versions. One's called pipe CG. The idea here is that we overlap a single dot product with the matrix vector multiply and the preconditioner. There's also NBPCG, where we overlap the first dot product with the matrix vector multiply and the second dot product with the preconditioner. One important thing to know about all three of these, they're all equivalent to PCG in exact arithmetic. There are a couple other variations of PCG methods that people have worked on that try to get better performance at scale. But at least for now, I haven't looked into those too much. So this is the NBPCG algorithm. And there are two key things I wanted to note with this. The first is that they have the ability to overlap the dot products. So we note, say for here, where we apply the preconditioner. Before that, we have a dot product, but the preconditioner application does not depend on the result of the dot product. So we can start a non-blocking Allreduce, we can apply the preconditioner, and then we can call a wait to get the result of this non-blocking Allreduce. So ideally, this will allow us to hide most of the cost of the Allreduce, as well as to limit the impact of noise. And the second thing to note is that when you rearrange these methods, you end up with additional vector operations. But we can use merged vector operations to limit the cost of this. If you do this kind of the naive way, you would do this first vector operation, you would load P and U, you do the second one, load S and W, and then in the third one, you'd load P and S again. If you merge this and do this one element at a time, you can do 4 loads instead of 6. And in general, the loads and the stores are the costly part of these operations. the computation itself is pretty cheap. And PCG does something similar to this to limit the impact of the extra operations. So this slide basically shows kind of a summary of these methods and the costs. In particular, we note that the reads, that number is pretty similar on all of the different methods. The writes, however, increase quite a bit, or they increase a bit for the other, the rearranged methods. And we see that L56 PCG and NBPCG have about the same amount of work as far as reads and writes go. The computation we can see goes up a bit as we do more, as we have to rearrange the methods more, but this computation is not too expensive. We should also note that PCG and NBPCG have 2 Allreduces per iteration, while L56 PCG and PCG have 1 Allreduce per iteration. All 4 of these methods have 1 matrix vector multiply and 1 preconditioner application. So since these non-blocking methods depend so much on the non-blocking Allreduce, it's important to go over this for a minute. The Allreduce itself, as you probably know, it combines values from all processes and distributes the result back to all the processes. This Allreduce becomes a bit more expensive at scale, but in general, a lot of systems have ways to limit the cost to make this fairly efficient. For the non-blocking Allreduce, this was introduced in MPI 3.0. Unfortunately, there aren't necessarily good implementations everywhere. One of the issues we've run into on Blue Waters is that one way you can technically implement it is basically by setting up the reduction when you call MPI Allreduce, and then when you call the weight, call a blocking Allreduce. So you don't really get the benefit of the non-blocking Allreduce. So basically one of the issues we're dealing with right now is that we need to find an efficient non-blocking Allreduce, and we need to verify that it can actually overlap communication and computation. That said, since we don't have a good non-blocking Allreduce, it's another reason why we need to do performance modeling. So the general idea behind performance modeling is we want to better understand the theoretical performance of PCG. In particular, we want to model the key routines that we've talked about. We also want to model issues that limit performance. For example, model noise and how that impacts the methods. And additionally, this allows us to validate both the performance model and our implementation which runs on Blue Waters. So as far as the model goes, we use LogGP model to model the parallel computation. And to generate the model parameters, we use a modified version of the stream benchmark, and we use the net gauge benchmark to generate the communication parameters. So these tests are run on Blue Waters, and we base the parameters on Blue Waters also. Basically, this is a Cray XE6 at the University of Illinois and the National Center for Supercomputing Applications. Key thing to note is that there are 16 floating point units per node, and we use 16 cores per node for our tests. As far as the linear systems go, we use 5-point Poisson matrices. We've tested some larger matrices, but in general, the other ones with more points generally have a higher cost for the matrix vector communication. So this is pretty good for illustrating the methods. We use block Jacobi with ILU as a preconditioner. Basically, we use this because it's pretty simple. Later, we're going to look into some more complicated preconditioners. We do performance runs on Blue Waters using up to 32K cores, 16 cores per node, and we do 20 iterations of PCG per test. And from time to time, we also use some various to try and locate the sources of load imbalance. So this slide shows the computation parameters we generate. We determine parameters both for when data fits into L2 cache and when it does not. For this, we use a heavily modified stream benchmark. Basically, it's an MPI version. We also add kernels for XP, AYPX, and a local dot product. Basically, this is to make sure that all of the tests that we focus on use 2 arrays so that all the tests fit into cache or don't fit into cache when we run them for a given array size. And also, when we assume that 3 equals right, we get reasonable parameters. In particular, for 16 cores, we see this dark blue line. We see a pretty clear two pretty clear sets of parameters, one when it fits into cache, one when it does not. The compute parameters aren't quite so nice. For one core, we see this green line. For 4 cores, we see this kind of jump up, and we see an even bigger jump for 16 cores. This is something we need to look into a bit, but if you look at the cost of these stream computations, you can see that for smaller array sizes, the copy and the AXP are pretty similar, and they're fairly similar for the largest, but in between there's kind of a big gap. And basically that ends up going into the compute cost. So that's something we'll need to look into a bit more. This is the LogGP model that we use. The basic idea behind this is that when we send a message, we have some send overhead. We then have a gap per byte cost. Once we have the message fully injected into the network, there's a latency cost until it arrives at the receiving process. And then there's some receive overhead. Once we've finished injecting the message into the network, we have this G cost before we can send the next message. But basically, this LogGP model allows us to better model overlapping communication and computation. So these are the communication parameters we got from NetGauge for message sizes ranging from 8 bytes to 128 kilobytes. These parameters are generated on Blue Waters with 1 process per node on up to 1K nodes. And we basically use the average size of parameters generated by each process for each message size. So the send and receive overheads should be constant. Instead, you can see that they're increasing fairly steadily. We went back and looked at the NetGauge paper on generating LogGP parameters, and they had some results showing similar behavior. So that's one more thing we're going to need to look into a bit more. The latency and the gap between messages, those both gave pretty constant costs after some initial variation at the beginning. And the gap per byte costs were pretty constant also. And all these times are in microseconds. And basically, we feed these and those stream parameters into the model. So next, I want to talk about how we model these. Model PCG, and basically assumptions that we made. For the Allreduce, we use a recursive exchange implementation with log base 2 of p steps. We assume that the blocking Allreduces causes all processes to block for the full duration of the reduction. And at least for the time being, we ignore the impact on the number of hops. Eventually, we need to probably look into this a bit more as far as modeling contention, for example. But for now, we ignore it. For the non-blocking Allreduce, we block for the send overhead at the beginning of the reduction and the receive overhead when wait is called. But in between, we assume that we can do computation while the remainder of communication occurs. And if the Allreduce isn't finished when the wait is called, then we have a synchronization cost. For the merge vector operations, we break these costs into read, write, and compute costs. For the matrix vector multiply, we assume we have a CSR matrix with row partitioning. We assume that each process has about the same amount of communication. We use the LogGP model basically for the sends and receives. And in general, we note that if L is greater than G, we get more overlap between communication and computation. Unfortunately, the way the Blue Waters parameters works out, there's not too much overlap. And for the block Jacobi LU preconditioner, we model this using the block diagonal cost of a matrix vector multiply. Basically, this was just a quick and dirty model for this. We're going to go into it in a bit more detail in the future. So now I have some model predictions. Basically, the graphs on the top show the predicted runtimes. The graphs on the bottom, they show the ratio between standard PCG and the other variations. We can in general see that it predicts that there's going to be some decrease as we increase the core count, or some improvement. On lower core counts, for larger core counts, we see that these methods are predicted to outperform the standard PCG method. And also I should note, you see a jump here. Basically, the model predicts that PCG will fit into L2 cache, while the other methods will not. So it performs a bit better for that particular core count. For the vector operations, we get about the behavior we expect. PCG is the best. The NBPCG and L56PCG are a bit slower, and PipeCG is slower than those. The model also predicts that basically the cost for the Allreduce is basically equal to the initial send overhead and the final receive overhead, and otherwise it basically overlaps everything. For PCG and L56PCG, you don't really get any benefit. It's basically the full cost of an Allreduce. So this kind of breaks down the cost of the NBPCG method. In general, we see that the matrix vector multiply is the most time-consuming part. We see that the vector operations and the preconditioner are also pretty time-consuming, and the Allreduces are fairly small. Looking at the matrix vector multiply breakdown, we see that there's some communication that it predicts, but not too bad compared to the computation. And in general, we see that as long as the computation is greater than the communication, we get a good overlap for the Allreduce. But if there's more communication than computation, there's a synchronization cost. So these are some results from Blue Waters. Once again, the graphs on the top are the runtimes, the graphs on the bottom are normalized with respect to PCG. Basically, since we don't have a good non-blocking Allreduce implementation, we basically get the behavior we would expect. The variations of PCG with more vector operations end up being more time-consuming. So to really get good results, we're going to need to try and find some way to get a good non-blocking Allreduce. If we do a breakdown and see where time is actually being spent, we can pretty clearly see that the matrix vector multiply is where most of the time is being spent. Down here where the black line is, that's the wait for the Allreduce. We can see that there's some decent time there, and we can see that it varies a bit. We can also note that in the matrix vector multiply that the communication for the red and the blue line, those are pretty significant. So we need to investigate that a bit more and see if we can find a way to make those less costly. For the bottom two graphs, we insert barriers after each of these operations to try and figure out where the variation in performance is coming from. And in general, we can see that the matrix vector multiply is causing there's a lot of blocking that's going on in there. There's some in the preconditioner. In general, the Allreduces themselves, there's not too much performance variation in those. So also, since these non-blocking methods take advantage of merged vector operations, I want to show a comparison of the optimized merged vector operations compared to doing separate vector operations. The graphs on the left are for a 16K by 16K grid, which basically ends up with a 256 million row matrix. The ones on the right have about 1 billion rows in the matrix. And you can see that especially for PCG and NBPCG. There's some pretty significant, savings by using the merged vector operations. Basically, it goes up to about 35% on PipeCG, and we see about up to 25% on NBPCG. So we also wanted to compare the model versus performance results. In general, for all the computation-related modeling, it's pretty close to the model, and the actual results are pretty similar. For the Allreduce, we see big differences, but this is because the model is predicting that we're going to have good overlap, while in the actual implementation, we don't have a good non-blocking Allreduce yet. The one place where we have some pretty significant differences is in the MatVec communication. Basically, our guess here is that we're not modeling contention, and that's apparently having a sizable effect. So we will need to update the performance model to take this into account. So far we've assumed that all processes can perform each computation and send each message in the same amount of time. This isn't realistic behavior, especially on large core counts. So there are a lot of sources of computation noise and communication noise. In general, there's not, in general, they can have a pretty sizable impact. So it helps if you can have methods that can deal with these well. And in general, noise throughout PCG limits the performance by causing all processes to wait for the slowest process at sync points. So we try to update the performance model to take into account noise. So we model the parameters with noise by using a normal distribution to represent the impact of noise, and we use a perturbed cost for the model parameters for each computation or message. We were able to implement a simple model so far. Basically, this adds the worst case performance for all processes to the cost of each step of the blocking methods. For the non-blocking methods, it assumes that the different processes don't get too far apart. And we basically add in the average noise for each step. Eventually, we want to do a more detailed model. Basically, we want to track or model the performance of each process separately and try to get a bit more detail in the model. So these are the results of the simple model. In general, when we look at the normalized graph, we can pretty clearly see that NBPCG is predicted to outperform PCG. We also see that PipeCG, while not immediately outperforming PCG, should in time. And in particular, once data fits into L2 cache, we get some pretty big performance benefits. So in conclusion, the model shows that non-blocking methods provide the potential to give speedups at extreme scales. In practice, we don't really see much benefit due to the lack of efficient non-blocking Allreduces. And in general, the ability of these non-blocking methods to perform well despite system noise might provide the biggest benefit in the future. There's a lot of work we need to do still, basically determine better communication parameters that take into account contention, come up with a more accurate noise model, and in general run larger tests as well as modeling the impact of different system architectures or more complicated preconditioners in the future. So these are a couple references, and that's pretty much it. Thank you.